All right, good morning, everyone, and welcome to Lecture 17 of 124103, where we are talking about heat. So in this lecture, we will talk about heat transfer, specifically two kinds of heat transfer, conduction and convection. So previously, when we started the topic on heat, we started by defining what temperature is. And we said that temperature is perceived as how hot or cold an object is. And we've seen that it's related to the speed of the molecules, so that the higher the temperature is, the faster the molecules in the object move, and that causes the expansion of the object in general. And then after that, in our second lecture, we talked about heat, and we defined heat as the energy, thermal energy that is transferred from one object to another due to a difference in temperature. And we've seen that if you bring two objects together and these objects have different temperatures, the heat or energy will be transferred from the hot object to the cold object, right? So we talked about how the temperature of the objects will change when heat is transferred. And we also talked about how the phase of the object can change, for example, from solid to liquid when heat is transferred. But we haven't really talked about how heat is transferred in the first place. So we started first by looking at what happens to temperature when heat is transferred or when energy is transferred, but we haven't talked about how energy or heat is transferred in the first place. So the next two lectures, lecture 17 and lecture 18, we'll look into the different mechanisms for transferring heat. And for this lecture, we will look at two mechanisms, conduction and convection. So we will compare and contrast these two mechanisms of heat transfer. And then we will look at how much heat, how we can quantify the amount of heat that is transferred by conduction and convection, looking at examples that are relevant to physiological and biological systems. Okay, so right, so let's start by looking at the three mechanisms for heat transfer. So there are three of them. I've mentioned two already, conduction and convection. And that's what we will talk about today. But there's a third mechanism for heat transfer. It's via radiation. That will be the topic for tomorrow's lecture. So here in the figures here shows you the three mechanisms for which heat can be transferred. But in all three mechanisms, it's important to remember what we've been learning so far, that heat is transferred only because of a difference in temperature, right? If you have two objects that are at the same temperature and you bring them in contact with each other because they're already at the same temperature, then heat will not transfer between them, because normally heat will transfer from the hot object to the cold object. So if they have the same temperatures to start with, then heat will not transfer between them. So heat will transfer only if you have a difference in temperature. And the direction for heat transfer is from the hot object or high temperature object to the cold object or low temperature object. And heat will transfer from hot to cold until the two objects have the same temperature, and we say that they are in thermal equilibrium. Right? So just keep these two concepts in mind, and they will come up often, especially this concept of difference in temperature. Right, so let's start by talking about the first mechanism, conduction. So in conduction, so I'll play this video and have a look at this video. I'll talk over it to sort of explain what conduction is. So conduction, I think all of us would have experienced in some form of another heat transfer by conduction. So consider a metal spoon. If you bring it close to the flame, we know that at some point we will feel the heat. We will feel the spoon getting hot. And this video just illustrates some paper clips that are glued to the spoon using a wax. So you can see that the paper clips, one after the other, they fall off as the wax melts. And that is a visualization of heat being transferred from the tip of the spoon closest to the flame. Let me just repeat that. So the heat being transferred from the tip of the spoon closest to the flame, being transferred along the length of the spoon. And so as each part of the spoon heats up, the wax melts, and that causes the paper clip to fall down. So notice how the clips don't fall down all at the same time, rather they fall down in sequence, showing you that the heat is being transferred, gradually from this point. And after some time, the person's fingers will feel the spoon becoming hot at this far end. So heat transfer by conduction requires a direct contact between the two objects that are at different temperatures. So you have there the flame, the hot flame, and the cold spoon. They need to be in direct contact for heat to transfer via conduction. The mechanism for heat transfer via conduction sort of happens microscopically. It happens within the material. And so we don't really see the heat being transferred from the tip of the spoon to the far end. Rather, we have to look at what's happening inside the material to understand how heat is being transferred via conduction. And so if you look at the atoms that make up the material, okay, again, in conduction, the two objects need to be in direct contact. So you have the flame being in direct contact with the metal spoon. The circles here represent the atoms that make up the spoon. Notice how as the flame heats up the spoon, the atoms gain thermal energy. So the atoms, individual atoms, become hotter, represented by the red section here. And we've seen last time that when atoms heat up, when they gain energy, they start to move and they start to vibrate. Okay? And as they vibrate, they collide with neighboring atoms, and when they collide with neighboring atoms, they share some of their energies, and the process continues. So as the atoms collide and transfer their energy to the neighboring atoms, the heat is from the flame is sort of transferred throughout the length of the spoon. And I guess this animation here, it's a better visualization. You can see there the tip of the spoon closest to the flame. The atoms there start to vibrate first as the atoms acquire the thermal energy from the flame. As the atoms near the flame vibrate, they bump into the neighboring atoms, and that transfers some of the energy, some of the heat to the neighboring atoms. The neighboring atoms start to vibrate, they collide to the neighbors, transferring some of the heat, and that process continues until heat is propagated until the far end of the object. Right? Okay, so that's sort of the visualization of how heat is transferred via conduction from a hot object to the cold object. So it happens microscopically inside the material. Right? Does that make sense? Yeah, so I think the key thing you need to remember and to distinguish between the other mechanisms of heat transfer is that in conduction, the two objects need to be in direct contact with each other, because then that's the only way that heat is transferred from the hot object to the cold object. Okay. Right. We can classify different materials according to how efficiently they can transfer heat via conduction. And we classify them according to their thermal conductivity. So the thermal conductivity, which we use the symbol small k, so that's just a normal lowercase k to represent thermal conductivity. It's a property of the material that determines how well it can transfer heat by conduction. And so every material will have its own specific value for thermal conductivity. It's just like specific heat capacity that we learned last time. Every material has its own resistance to heat transfer in the same way that every material has its own capacity to conduct or transfer heat by conductivity, by conduction, and we call that thermal conductivity. So according to thermal conductivity, we can classify materials as good thermal conductors or good thermal insulators. So as the name implies, thermal conductors, they are materials that can easily transfer heat by conduction, meaning they have high values of thermal conductivity K. So the higher the value for thermal conductivity, the easier it is to heat up that object, because the easier that object will acquire thermal energy. And a good example of thermal conductors are metals. And metals are good conductors because there are a large number of electrons that are free to vibrate. And we've seen in the animation previously that transfer of energy by conduction is through the vibration of the atoms. So if you have a large number of electrons in the atoms that are free to move, then they can easily collide with neighboring atoms, and they can easily transfer their heat, their thermal energy to neighboring atoms. And that's why metals are good conductors of heat. On the other hand, insulators, they have a small value for the thermal conductivity. So the smaller the value for K thermal conductivity is, the slower the object heats up. And that's because the slower heat is transferred via conduction. A good example of insulators are given here. So air and wood, paper, wool is also a good thermal insulator. Just think about what materials they use to manufacture thermal clothes, for example, or down jackets. So those are these are some examples of thermal insulators. Good. Okay, so just a conceptual question, just to make sure we grasp the idea behind conductivity, heat transfer by conduction, and thermal conductivity. So given your experience of what feels colder when you walk on it, which of the surfaces given here, A, B, C, would have the highest thermal conductivity? Okay, so is it rug, steel surface, a concrete floor, or does it not have nothing to do with thermal conductivity? So what do you think? Okay, so I see there rug or steel, and also steel surface, right? Okay, so thermal conductivity is a property of the material that determines how fast heat is transferred. Oh, yep, good. Okay, good, Hannah. All right, good. You corrected yourself, because so then everyone will have the right answer. It's steel. Steel will have the highest thermal conductivity because the higher the thermal conductivity, the easier it is for that material to heat up. And so, of course, the opposite is true. The higher the thermal conductivity, the easier it is for that material to cool down as well. So it's all about heat transfer. The higher the thermal conductivity, the easier it is to transfer energy in and out of that material. Okay, so steel should have the highest thermal conductivity because we feel coldest when we're standing on steel. And I said earlier that thermal conductivity is a property of the material. Every material has its own fixed, it's a constant that every material has. So if you Google thermal conductivities for each of these materials, for example, or look it up at the table and compare their values, you'll see that steel does indeed has the highest value for thermal conductivity. Okay. Yeah, wool has a very low thermal conductivity, 0.04 joules per second times meter degrees Celsius, and that's why wool is a very good insulator. It keeps us warm because it prevents us from losing heat to the atmosphere. All right, good. Okay, now if we will quantify the amount of heat transferred via conduction, so let's see how much or the amount of heat that's transferred via conduction. So consider now these two objects, so a hot object and a cold object. So the condition is that two objects need to have different temperatures to begin with, and then those two objects need to be in direct contact with each other. So say you have this hot object and this cold object, and they are in direct contact with each other. Heat will now transfer from the hot object to the cold object. So if we think about it logically, right? So the amount of heat that's transferred from the hot object to the cold object will depend on the thermal conductivity, right? Okay, so we've just learned that the higher the thermal conductivity of the object is, the faster heat will transfer, and therefore the more heat will transfer the higher the thermal conductivity. And so it would make sense that the higher the thermal conductivity K, the more heat should be transferred. So you have this direct relationship between the thermal conductivity K and the amount of heat transferred Q, right? Also, if you think about it, the larger the area that's in contact between the two objects, the more heat can be transferred between the two objects, right? Because then the bigger the area that is in contact, the more heat can transfer. The thing to important here to remember here, it's that the area that's in contact that's important. So if you notice here, the actual area of the hot and cold objects, they're bigger than the area that are in direct contact, the area that's in direct contact. And what matters is the area that's in direct contact, because it's over this area that's in direct contact that heat will transfer from hot to cold. And the bigger the area that's in direct contact, the bigger the amount of heat that's transferred. So you see this direct relationship between the area that's in contact and the amount of heat that's being transferred. Okay. Also, if you think about it, the bigger the difference in temperature between the two objects, the bigger the amount of heat that's transferred, right? So if this object is very, very hot and the other object is very, very cold, you have a big difference in temperature, so heat will easily transfer from hot to cold. Okay. The reverse, if the two objects are at the same temperature, then no heat is transferred between them, right? And so it makes sense that the bigger the difference in temperature, the bigger the amount of heat. So you have this direct relationship between the difference in temperature and the amount of heat. So just take note, delta T Here, it's not the change in temperature, rather it's the difference in temperature. So you determine delta T as the hot temperature minus the cold temperature. Okay. Right, and then if you think about it, the longer the two objects are in contact with each other, the more heat is transferred, right? So you have this t, small t, which gives you the time over which the two objects are in contact and over which heat is being transferred. So if you think about it, the longer the two objects are in contact with each other, the bigger the amount of heat is transferred between them. So you also have this direct relationship between the time of heat transfer and the amount of heat transferred. Okay. And finally, we have this distance d. Okay. So this distance d is how far the objects are from each other, or how thick the object is. So if you think about it, the thicker the object is, the less heat is transferred, because then heat needs to travel over this distance. Okay, so the farther the heat needs to propagate or travel through, the smaller the amount of heat is transferred, right? And so you have this inverse relationship between the distance d, or the length. D is the length or thickness over which heat is transferred, so some distance d. You have this inverse relationship between the thickness or distance and the amount of heat transferred, right? Okay, and so you have this equation that relates the amount of heat transferred to the different parameters. Thermal conductivity K, the area over which the heat is transferred, difference in temperature, delta T, hot minus cold temperature, the time, length of time over which heat is transferred, and the thickness or distance D over which heat is transferred. Right? Okay, so I hope the equation makes sense. If you think about it logically, I hope that the equation makes sense. Sometimes we rearrange this equation so that we want to know the rate of heat transfer, or how fast heat is being transferred, in which case if we rearrange this equation and get the rate, then we divide both sides with the time. So this time here on the right side disappears, and you have here the rate of heat transfer. So when we say rate, it's something divided by time. So when we say rate of heat transfer, it's the amount of heat transferred over a period of time t. And notice how the time t disappears on the right side of the equation. So it's essentially the same equation for that we've seen here, except that the time t now goes to the left-hand side. And you have the amount of heat divided by the time, giving you the rate of heat transfer. And so the rate of heat transfer still depends on the thermal conductivity K, the area, the difference in temperature, delta T, and the thickness or distance D. Right? Okay, I guess the best way to look at this equation and maybe understand this equation is to look at an example of how we relate the amount of heat to the different parameters that affect how much heat is transferred. So let's look at this example about the chicken eggs. Chicken eggs must be kept at 38 degrees Celsius for the chickens to hatch, or the egg to hatch. Given that the thermal conductivity of an eggshell is 0.45 watts per meter per Kelvin. Okay, so this is a new unit I guess I need to introduce. So watts is a new unit that we encounter, watts or capital W. It's the unit for rates of heat transfer. So the basic or standard unit for watts is joules per second. Joules, of course, is the unit for heat, Q, and second is the unit for time. So it means, so for example, the rate of heat transfer here is 0.45 watts. It means that every second 0.45 joules of energy is being transferred over a 1 meter area, a 1 meter distance, and a 1 Kelvin difference in temperature. So that's what the watts, the unit watts means. It's joules per second. It's the amount of heat transferred per second. Yeah. So the thermal conductivity of the eggshell is 0.45 watts per meter per Kelvin. And the average surface area of an egg is 0.011 meters squared. The thickness is 0.005 meters. We want to know how much heat is lost if the egg is left for half an hour on a 24 degrees Celsius day. Okay. Right, so let's imagine this scenario. So you have the egg, right? The egg has a temperature of 38 degrees Celsius. Okay. Right, so we'll assume that the temperature of the egg is uniform all throughout, 38 degrees Celsius, and you have the surface area is 0.011. So this whole area, the surface area of the egg, 0.011 meters squared. The egg is 0.005 meters thick. So that means you have this thickness right. So you have this thickness, that's thickness D, 0.005 meters. Okay. Right, and then the outside temperature is 24. So outside of the egg, you have 24 degrees Celsius, the temperature of the egg's environment. Yeah, and the egg is left for half an hour. So we have there the time, half an hour or 30 minutes. We have to work in seconds. So 30 minutes is 1,800 seconds. 1 hour is, or 60 minutes is 3,600 seconds. So 30 minutes is 1,800 seconds. Right. Okay, you have thermal conductivity K, small k is 0.45 watts per meter per Kelvin. Right, so if you imagine the scenario here, because there's a difference in temperature, so you can also then take the difference in temperature, hot minus cold, that will be 38 minus 24, 14 degrees Celsius. That's also equal to 14 Kelvin. Because we've seen that if you're getting the change in temperature or the difference in temperature, as long as it's a delta T, Celsius is equal to Kelvin. So 14 degrees Celsius is also equal to 14 Kelvin. Okay, so if you imagine the scenario here, you have an area of 0.011 meters squared and a thickness of 0.005 meters. Right. So imagining the scenario, you have an egg that's at a different temperature to its environment. So there's a difference in temperature. We've seen they're of course in direct contact because air is just all around the egg. So heat will transfer from the hot egg to the cold environment. but the heat transfer will occur throughout the surface, the whole egg, throughout the whole egg. In short, throughout the whole area, 0.011 meters squared, right? Because we'll assume the picture shows that the egg's on the ground, but we'll sort of assume that the egg is sort of suspended in the air, so that heat is transferred all around the egg throughout its surface area, 0.011 meters squared. Okay, and as heat is transferred, it has to pass through the eggshell. Okay, and the eggshell has a thickness of 0.005 meters. So you have this distance over which heat needs to travel from the hot egg to the environment. Okay, right? So that's the scenario there. So clearly it's heat transfer by conduction. Q is equal to Ka delta T times time divided by distance. Right? Okay, so comparing the equation and what's given, we actually know everything. So it's just a matter of substituting the numbers. So you have K 0.45 times A 0.011 times delta T 14. So I use Kelvin for the units of delta T because the unit for the given conductivity, thermal conductivity, is in Kelvin as well. So just for the sake of consistency of units, I put my delta T in Kelvins, but it doesn't matter if you still use Celsius because Celsius and Kelvin are the same if you're doing delta T. And then time, 1,800 seconds divided by the thickness of the egg, because that's the thickness is the distance over which heat needs to travel for it to transfer to the environment. So that gives you the amount of heat transferred over 30 minutes to be this much, 24,948 joules. All right, so there's a note there here that I said that I put here. Just make sure your units are consistent, and the thermal conductivity is a constant number, and the unit is often given together with that constant number. So you can use the unit for the thermal conductivity to determine what units you need to do, but the safest is just to convert everything to SI, or standard units, base units. So you have their meters, so your distance should be in meters. Kelvin, temperature should be in Kelvin, but as I've said, temperature difference in Kelvin and Celsius is the same. So it's not so much strict in terms of the unit for temperature. The unit for time must be in seconds. Okay, it has to be in seconds because watts is composed of joules per second. So time should strictly be in seconds. Yeah. All right. Cool. So are we happy with this solution for this example? Good. All right. So that's heat transfer by conduction. So now let's look at the follow-up question. It says that, so we've left the egg for 30 minutes and we determined that over the time, this much energy is transferred. So the egg has lost 24,948 joules of energy because it's transferred to the environment. Now, the next question is calculate the associated temperature drop for an egg if the egg has a mass of 57 grams and the specific heat capacity of the egg is 37 kilojoules per kilogram per Kelvin. Okay, so in the previous question, we determined how much heat is transferred, the amount of heat that's transferred. Now in this question, we're being asked how much the temperature of the egg will drop as a result of 24,948 joules of heat being transferred to the environment. Right, so how do we solve this? So temperature drop, that means there's a change in temperature. Okay. And last time in the last lecture, we already saw an equation relating to the change in temperature, which is Q is equal to MC delta T, right? So notice, remember that the delta T in this equation is the change in temperature as a result of heat Q being transferred from the hot object to the cold object. Okay. And that's why the mass is given, because here M is the mass and the specific heat of the egg is also given, because C in this equation specific heat. We want to find delta T, change in temperature, which means we need to rearrange Q equals MC delta T to isolate delta T. And so we divide the equation both sides by M times C. That cancels MC on the right-hand side, giving us the equation for the change in temperature as Q divided by MC. Right. So what Q to use? Q is the energy, amount of energy that's transferred, which resulted to the change in temperature delta T. So that means that's the Q that we calculated in the previous question, because this much energy is transferred from the egg to the environment because of the difference in their temperatures. And as a result of this amount of Q transferred, we have this change in temperature delta T. So the mass of the egg has to be in kilograms. We divide grams by 1,000, and so you have this should be 0.57. Yes. 570 divided by 1,000 is 0.57 kilograms. Okay. Times the specific heat, 37. So I'm 37 kilojoules means, kilo, prefix kilo is 10 to the 3. That's why 37 kilojoules becomes, it should be 37,000. Yeah, 37,000 joules. Okay. 37 kilojoules, kilogram, Kelvin to the -1. Kilo is times 10 to the 3 or times 1,000. And that's why 37 kilojoules, what's originally given, becomes 37,000. Right? So just please correct the mass. 570 divided by 1,000 should be 0.57. So you have a change in temperature. This might be wrong, so let me just double check. 24948 divided by 0.57 times. Yeah, it should be 1.2 Kelvin because because of this extra zero that I had here. Right, so the change in temperature should be 1.2 Kelvin. Right. Are we happy with this solution? Good. All right, cool. So that is, so here we've seen heat transfer by conduction in this example. And then as a result of heat being transferred, we also saw the change in temperature for a given amount of heat that's transferred. Yeah, so it's important to know the meanings of delta T in equations. They can mean different things. So delta T in Q equals MC delta T, and delta T in the conductivity equation means different things. In the first equation, Q equals MC delta T is the change in temperature as a result of heat transfer. And in the second equation, delta T means temperature difference. And it's the temperature difference that allows heat to be transferred via conduction, right? Yeah. So I think it's really important to distinguish between these two delta T's in order to know which equation to use in solving the problem. Okay, so the second heat transfer mechanism is by convection. So in convection, heat is transferred via the movement of a fluid, of liquid or gas. Okay? So in conduction usually happens between solids because then the solids are in contact. But conduction can also happen between liquids, right? When you mix two liquids together, then they are in direct contact, then you have there some form of conduction. But convection happens mostly in liquids or gases, because in convection, the material needs to move in order for heat to be transferred from one point to another. So boiling water, for example, you'll see the water is bubbling and moving, and through the movement of the water, heat is transferred throughout the pot, making the liquid uniform in temperature. Okay, here is a image of a room, like an infrared camera image of a room. You have a heater on one part of the room. Notice as the air near the heater heats up, that the air molecules start to move. They bring with them their thermal energy, and as they move, they transfer the energy throughout different parts of the room. Okay, so you can see there the actual movement of the air particles within the room, and it's the movement of these air particles that will bring the thermal energy to different parts of the room. Okay. So you can either have natural convection, like the natural movement of particles, fluid particles, as a result of the difference in their densities between cold and hot particles. Or you can also have forced convection. That's when you use a fan, like to drive the air particles around the room, for example. Right. So the key distinguishing feature between conduction and convection is that in convection, you have the actual movement of particles, and it's the movement of these particles that will transfer the energy to different parts of a particular space, like the room. Whereas in conduction, the two objects should be in direct contact with each other in order for energy to flow or to transfer from the hot object to the cold object, right? Okay, so if we again look at an equation to quantify the amount of heat transferred by convection, notice it's the similar form. So in conduction, the heat transfer equation is Q is equal to Ka delta T times time divided by D. Okay. For convection, notice it's a similar form. So you also have the area. So the amount of heat transferred also depends on the area, because if your particles travel over a large area, then you will transfer a larger amount of heat. Again, you have this difference in temperature delta T, hot minus cold. The bigger the temperature difference, okay, the more particles move from the hot part to the cold part, and the bigger amount of heat is transferred. And also you have time. So the longer the longer you use a electric fan, for example, the more heat is transferred around the room. Okay, so it's a similar parameters. You have A, delta T, and T. You also have this dependence on the material. So for conduction, you have thermal conductivity K. For convection, you have Q. And Q is called convective heat transfer. And please correct the slides on stream. I think on stream it's still given as K, but that's in fact Q for convection. It's called convective heat transfer coefficient or film coefficient. So it replaces the thermal conductivity. The thermal conductivity is just for conduction. For convection, we represent that by Q, convective heat transfer. Okay, and the main difference between the conduction and convection equation is that in convection you don't have this dependence on the thickness. Okay, right? In conduction, the two objects need to be in direct contact with each other, and it's over this distance that they are in contact that heat is transferred, and that's why you need this distance d in conduction. But in convection, okay, the cold part of the room, for example, the hot particles in one part of the room will just randomly travel around the room. So there's no set distance d to talk about. And so heat transfer by convection doesn't have this thickness or distance relationship. So it's just QA delta T times T. We can also talk about rate of heat transfer in a similar way as the amount of heat transferred over a particular time t. So you have Q over T, Q divided by T for the rate. And that means the time T disappears from the right-hand side of the equation. So amount of heat for the first equation, rate of heat transfer for the second equation. Okay. All right. Take note again, delta T is again the difference in temperature, because that's only when you can have heat transfer, is when you have a difference in temperature, hot temperature minus cold temperature. Okay. Right. And so let's look at an example of how we can solve heat transfer by convection. So this time we're looking at emperor penguins who live in extreme conditions, and to survive in a very cold environment, the penguins tuck their flippers close to their bodies, where their skin temperature is 35 degrees Celsius. Okay. What is the rate of heat loss by convection through the flippers if they are not tucked in on a windy day and the outside temperature, the temperature of their environment is negative 20 degrees Celsius? The surface area of the flipper is 0.05 meters squared, and the heat transfer coefficient is 0.03 watts per meter squared per Kelvin. So you can imagine, so in a windy day when the flippers are not tucked in, so say this is a flipper. So, right, and you have, so you have wind blowing over the flippers, okay? And as the wind, so you have the wind, the air particles, blowing over the flippers, and as the wind blows over the flippers, the wind, with the air particles in the wind, of course, take some of the heat from the surface of the flippers and transport that to the environment, to the atmosphere. And that's why you can think of this as heat transfer by convection. I guess the keyword there, it was a windy day. So you have air particles, air molecules that are moving around the flipper, flippers, and it's the movement of these air particles that take away the heat from the flippers and transport that heat to the environment. Yeah, it's if it were a still day, it was not windy, and the flippers were just there sitting there in still air, then you can treat that similar to the egg that's just sitting there in the atmosphere, and then you can say that there's heat transfer by conduction. So in a way, there's also some heat transfer by conduction here, because the flipper is in direct contact with the cold air outside. But in this particular example, we are more concerned about the amount of heat that is transferred by convection as the air particles brush against the flipper. And as that happens, the heat is transferred. So say you have wind. So I don't know how to draw the wind air particles carrying heat away from the flippers. Okay. So we assume that the whole flipper is exposed. So it's the whole surface area that's exposed to the wind. So heat will be carried away throughout this area. Okay, so we're given the area 0.05 meters squared. And the temperature is different between the flippers. So temperature is 35 degrees and minus 20 degrees. So we can get the temperature difference. So you have 35 degrees Celsius for the flippers and negative 20 degrees Celsius for the air particles in the wind. So you get the difference in temperature as the hot minus the cold temperature. So make sure you include the negative sign. Right. And that gives you a temperature difference of 55 degrees Celsius. That is, of course, equal to 55 Kelvin as well. Right. And then you have here the convective heat transfer coefficient 0.03 watts per meter squared per Kelvin. Okay. So looking at the equation for heat transfer by convection, we actually were given everything. QA delta T, T, right. So we're not given the time. All right, so we don't know what time small t is, but the question says rate of heat loss. Okay, so rate of heat loss, that means we don't need the actual time. What we need is actually Q divided by time, which is QA times delta T. Right. So what we need is actually the rate, Q divided by time, or how much energy is lost per second. Right. So the coefficient of convection 0.03 times the area of the flipper. So we're assuming that heat is lost throughout the whole area because the whole flipper is exposed to the wind, times the difference in temperature delta T. Okay, that gives us the rate of heat loss of 0.0825 watts. Okay, so remember again, watts is joules per second. So 0.0825 joules per second means that every second, the flipper is losing 0.0825 joules of energy, of heat. All right. Okay, are we happy with the solution to this example on convection? Yep, good. All right. Are there any questions about conduction and convection? Right. Knowing how they're different. Yeah. In some scenarios, it could be that both heat transfer mechanisms are present. So one mechanism doesn't have to be isolated from the others. So we can have conduction and convection at the same time. And so in those cases, the overall amount of heat transferred will be from the combination of those two mechanisms. When solving problems, it's easy to identify whether we would want you to solve that by convection or conduction, depending on what's given in the problem. A clear way is if we give you the the thermal conductivity, then that's sort of a clue that the heat transfer mechanism there is thermal conduction, is conduction. Yeah, and keywords like you have the movement of fluids around the object sort of gives you a clue that it's heat transfer by convection. Or if we give you the heat transfer coefficient for convection, then that's also sort of a clue that it's heat transfer by convection. So I guess picking out clues from the problem will give you an idea of whether it's heat transfer by convection or conduction, or whether we want you to consider both. All right, but that wraps up our lecture on heat transfer by conduction and convection. We've seen these two equations and we've seen how to use these equations. And in the workshop, you'll have more practice looking at those equations and applying those to problems. So you have here, it's just one scenario of a pond with a frozen surface. And we want the first question asks us to find the heat transfer rate by conduction. Second one is how long it will take to lose this certain amount of heat to the environment by conduction. And here we have a question about relating also. This third question is a little bit more complex, and it will require you to draw concepts from previous lectures on density, for example. And yeah, and the last one is something special that we will look in more detail in the next lecture, with evaporation, combining phase change and heat transfer. But have a go at the workshop. I think, oh, good. I think for the first time we finished the lecture just on time. So maybe we can come back at 10:20. Maybe I'll give you around 20 minutes, because I'd like to spend some time talking about the solutions to question C and question D. And so maybe I'll devote more time talking about those. So maybe 40 minutes to talk about the solutions. Are you happy with 20 minutes to try the worksheet and look at the questions? Yep. Okay, yep, good. So 10:20 will resume. I won't end the chat. I mean, I won't end the Zoom, but I'll put myself on mute, and at 10:20 I'll talk about the solutions to the workshop.